Today's problem was submitted by a viewer, and it says, for how many positive integers n is n to the 4 plus 4 a prime number? So I know there's results about, it's about like prime numbers mod 4 or something. Or not primes mod 4, of powers of number, like squares mod 4 or something. I'll have to think about this. I mean, maybe we could come up with a few examples. So n to the 4 is equal to 1. 16, 3 to the 4 is 81, 4 to the 4. That's not right. $256, I should have known that. So n to the 4 plus 4, we've got 5, 20, 85, 251. I've been really tired the last couple days that I've been doing problems, probably because I'm jet lagged. 260. So, okay, I think the key to this is going to be looking at the last digit. So, of course, that's prime. But if the last digit of n is 2, suppose n is equal to 2 mod 10. N to the 4 is equal to 6 mod 10. And so then when you add 4, well, I mean, it's kind of obvious that if n is even, this won't be prime, right? The whole thing will be even. So let's forget about 2. What if n is equal to 3 mod 4? Then n to the 4 is equal to 1. Oh, yeah, not mod 4, mod 10. And so then when we plus 4, this is 5 mod 10, which this is only prime if it's equal to 5. Otherwise, it's a multiple of 5. So anything ending with a 3 won't work. What about a 5? Well, that's 5 mod 10. Okay, there's not much we can say about that if the last digit's 9. I'll come back to 5. 7 to the power of 4. That's 7 squared times 7 squared mod 10. Oh, forget about mod 10. 7 squared, 9. 9 times 9 is 1 mod 10. So 7 doesn't work either. And 9 to the 4, that's 9 squared times 9 squared, which is 1 mod 10. So that also doesn't work. So what about the digit Oh, what about if it ends in a, yeah, if it ends in a 1, if n is equal to 1 mod 10, then this number is 5 mod 10. So which one are you missing? 3. If it ends in 3. Oh wait, no, it's this. This is also going to be 1 mod 10. Oh, sorry, no, it's not 3. It's not 3 that broken, it's 5. N is equal to 5 mod 10. Wait, yeah, okay. So n to the 4 is also 5 mod 10. So n to the 4 plus 4 is 9 mod 10. What about the, let's test the first one. 125 times 5. $725 plus 4, $729. That's divisible by 3. What if we say n is equal to 10k plus 5, n to the 4, 10k plus 5 to the 4, n to the 4 plus 4, 10 to the, oops, 10k plus 5 to the 4 plus 4. Anything we can say about the digits of this number? Well, this is 5 to the 4, 2k plus 1, 4 plus 4. Okay, so n cannot be even. It can't end in a 3. It can't end in a 7, can't end in a 9. Um, to the 4 plus 4. Anything we can say about this? Hmm. Well, what if I take this 5 to the 4 times 2k plus 1 to the 4 plus 4 and expand that and see if the result is always divisible by something. Okay. Um, 2k to the 4 plus like even. It's always going to be the last term for this. This will always give the same 729. Oh, I think I see it. Okay, let's expand this. 2 to the 4, 5 to the 4, k to the 4, plus 4 times 5 to the 4 times 2 cubed, k cubed, plus, oh, no. I'm going to keep going to see if, yeah, what I was saying again. I am tired. I am not thinking straight. What is 279 divided by 3? $93. What? Yeah, 93 times 3. So if k is a multiple of 3. Wait. Yeah, if k is a multiple of 3, we do not get a prime. But that doesn't rule out everything. Maybe I need to take a completely different approach. So if the last digit of n is 1, this can only be prime if n is equal to 1. What if I mean, really what I'm doing here, this is maybe a better way of seeing it, right? I'm setting n equal to an odd multiple of 5. Huh. I kind of want to try this for 15. 15 squared is 225, I think. $225 squared . 50625 plus 4. 50629. Is this prime? I'm going to cheat. $50629. Not divisible by 3. I mean, I've checked up to 37 now. How many positive integers is it a prime number? Okay, it turns out that 50629 is equal to 197 times 257. Both of those numbers are prime. So do we go up to 25 to the power of 4? This is 390629. This is also not prime. 577 times 677. I'm failing to see any pattern here. Like, how should we be able to deduce that n to the 4 plus 4 has some prime factor when they are this large? And 35 to the 4, we're getting into the millions here. Right? 35 to the 4 plus 4 is 1. 500629, which is not prime. 13 times 89 times 1297. Okay, I see it. No, I don't. No, I don't. I saw something up here when I was going through this, right? All of these are going to be multiples of 10. I mean, you can even see from the pattern we have going on here that there's always going to be a 0 before the 629. Is that even true necessarily? Oh my goodness. 5 to the 4 is not 725, it's 625. So it's 629 that we're looking for to divide. Which is not prime. 17 times 37. I mean, it looks like the answer is only for n is equal to 1. I just don't see, I don't see how to prove that. It looks like this is the only case, but I don't know. What did I did something completely wrong here as well. 5 to the 4 plus 4 is 625. 629, sorry. I don't know. Is there some factorization that we should be doing? N to the 4 plus 4. I mean, how do you factor that? Let's call this k squared plus 4. Then that's k plus 2i times k minus 2i. Let's call the square root of 2i, let's call that, well, what is it? It's square root of 2 times e to the I pi over 4. I mean, that's one of the square roots. If we take the 4 sort of diagonal numbers in the complex plane, take the ones that have angles 45 degrees away from the origin and a modulus of root 2. Those will all be raised to the 4th power and equal 4. Yep. And let's call them, Z1 up to Z4. So I have n plus, sorry, n minus z1, n minus z2, n minus z3, n minus z4, where these numbers are all the quartic roots of 4. Now I want to multiply these together in such a way that I want to group them so that the coefficients are all real. Maybe I shouldn't call these Zi. Let's call them Zm plus I pi over 2 times m minus 1. I'm going to group Z1 and Z3. No, Z1 and 4 and Z2 and 3. Okay, so this is n squared. Z1 plus Z4. Gives 2. Z1 times Z4 also gives 2. Z2 plus Z3 should give negative 2. And Z2 times Z3 should give positive 2. Okay, so does this expand to n squared, n to the 4 plus 4? I get an n to the 4, I get a 4. Those cancel. Those cancel. Okay. Well, if n equals 1, we get 5. We knew that. Okay, so the answer is only when n is equal to 1. Otherwise, there's the factorization. And so you just have to make sure that this is never equal to 1 unless n is equal to 1. This is clearly never equal to 1. When n is equal to 1, that's equal to 1. When n is 2, that's 4 minus 4 plus 2. And then it'll never be 1 again. Yeah, so I was correct. This is only prime when n is equal to 1. Otherwise, this is a factorization where neither of these numbers is equal to 1. That's it. I don't know, like, my instinct was just to go for the digit approach. Clearly, I mean, it worked for everything but an infinite number of cases. It worked for anything not a multiple of 5. There's a lot of stuff. There's a lot of stuff about. No, I mean, it's not really. It doesn't really apply here. There's stuff about powers mod 4 or something like that. I don't remember. Anyone who's taken like intro number theory might recall that better than I do. This isn't exactly asking about that, but hey, there we go. Yeah, obviously I wish I had gone straight for this, seen this factorization. This little detour through the complex plane was just, it was like a last attempt. Obviously, if you know how to factor this thing immediately, you're fine. I wasn't sure that this was going to lead anywhere going through this complex number thing, but maybe you can see what my goal was. You know, this was just like a random attempt. You know, it's not a difference of squares, of course, but everything is a difference of squares if you generalize enough. So here's this written as a difference of squares with, imaginary roots. And then I just basically did that one more time, but then rearranged these so that the coefficients in these products would all be real. And it just happened to pop out the factorization, which I suppose is kind of what they wanted from this question. Thanks for the submission. Thanks for watching.